Hi, my name is Alex Lopez, and this is my lab report for Physics 2211 Lab 4. So the purpose of this lab is to compare the predicted motion and the observed motion of a mass which is oscillating on a spring. We will analyze the forces acting on the object, as well as the changes in the different types of energies, including kinetic, gravitational potential, and spring potential energies. And we'll do that using a tracker video to track the position of the object over time, and then GlowScript code to plot that data on a graph, as well as calculate and plot the changes in the energies. The main physics principles that we're looking at in this lab are Newton's second law, so the momentum principle, as well as the energy principle, in which you can see the three formulas on the right for kinetic energy, gravitational potential, and spring potential. And the big idea here is that the total energy is the sum of those three energies, and the total energy will always stay the same no matter how the different energies change. So here's the actual video of the object oscillating on the spring. You can see the X and Y components of its position are being tracked on the right, and those data points are what were used in the graph in GlowScript. Here's the GlowScript code. You can see the initial positions on the left. The mass of the ball was given to us to be 0.402 grams. And then we have the gravitational constant. The spring constant was given to us, and the L naught was given to us to be 0.123 meters. And then the position vector is from the video that I just showed. And then down below that, we have L equal to the position of the ball minus the position of the spring. L hat is L over the magnitude of L, and then S is the magnitude of L minus L naught. And then we have the formulas to find the kinetic energy, gravitational potential, and spring potential energies, and then we add those up to get the total energy. And then on the right, we have the formulas for the force of gravity, which is the mass of the ball times g, and then the force of the spring, which is the spring constant times S times L hat, and then we add those to get the net force, and then the velocity and position update formulas. And then at the bottom we have the same formulas for the energies as on the left, but with the updated positions and velocities. And then we have the delta K, delta UG, and delta US being those updated energies minus their initial values. So here are the resulting graphs. On the right, you can see the X position and Y position versus time graphs. And for both of those, the experimental model is not exact, but it's pretty close to the model values. And then on the left, we have all the energies plotted. And the important thing is that despite all the oscillations in the delta K, delta UG, and delta US, the total energy is staying the same. The total energy is not changing. So to answer some final questions, is the energy principle satisfied? Yes, it is. As we could see in the last graph, the change in energy was 0 the whole time, and that's because the change in energy is equal to work, and there was no outside work acting on it, so there was no change in energy. And then for the periods of oscillation for the X and Y positions, for the period in the X position, I got 1.63 seconds, and for the period for the Y position, I got about 1.51 seconds. And that is significant because the period is part of the formula for the spring constant. So if that was different, then that would affect the spring force and spring energy formulas. And some sources of error, in the tracker video, the mass might not have been perfectly tracked at the same spot each time.